Unfortunately, we cannot cure cancer, nor can we cure diabetes, at least not in the upcoming years. And even if we did, traumatic accidents are still going to happen. According to the last studies, about 1.9 million Americans are living with amputations, and this number is expected to nearly double by 2050, with a rate of approximately 507 people losing a limb to amputation every single day. So, we decided to act upon these insights, leveraging EMG technologies to create an affordable and practical prosthetic hand. The journey of its implementation was not easy, passing through 3 different stages. First, the sensing circuitry, to get a clear EMG signal with the required info for certain movements. Then, the signal processing, to process each delivered signal and classify it to the suitable movement. Finally, designing and controlling the hand using the processed signal. Also, one of our system properties is that it's extendable, both in hand structure and the machine learning model. We designed them in a way that allows us to add extra sensors for the hand or increase the number of classified movements whenever needed. And without any further ado, let's dive in.
The EMG signal provides a representation for the muscular movement. Its amplitude lies in between 1 to 10 millivolts, making it a considerably weak signal. The signal lies in the frequency range from 10 to 500 Hz and most dominant in between 50 to 150 Hz, which makes it highly influenced by noise from multiple sources. So, there will be lots of work to do in amplifying and filtering the signal to make it clear enough to be processed. Thus, we built the following sensing circuitry, consisting of 3 stages. First, a pre-amplifier circuit, which will be the instrumentation amplifier. Second, filtering using a fourth-order low-pass filter and a fourth-order high-pass filter. Finally, a second stage amplification circuit, which will be the operational amplifier. We intend then to build the whole circuit into a constructible PCB, where you can easily add things upon it or remove them without affecting the remaining components of the circuit. Eventually, the output signal will go through an analog to digital converter to deliver a readable signal with suitable characteristics to be processed.
Now, we move to the signal processing unit. After getting the signal from the acquisition system unit, now we aim to classify the signal using some methodologies, which we will talk about them later in this video. To make a good model that has the capability to classify the movements, we divided our work into 5 sections: dataset choice, data visualization, selecting movements, data preparation and pre-processing, algorithm choice, and model training. First, we need to choose a dataset which is large, representative, and helps to solve the problem. The final goal is to create a global model from the chosen dataset that covers our input signal and can achieve an accepted accuracy. Prior to the searching phase, we decided to work with the Nina Pro datasets. In our model, we will be working on Nina Pro dataset 2 and 3. Our choice for the 2 datasets was based on our need of building a model that can successfully classify the sensed sEMG signal into the right movement, is responsive and fast enough. This implied using a large amount of data for the training procedure, thus using dataset 2 with 40 intact subjects. But the intact data can only be used as an approximation for the amputees data, hence the choice of dataset 3, which contain 11 amputee subjects. The large number of subjects comes side by side with a unique probability for these datasets, which is they have 5 repetitions for each movement, thus increasing the amount of data that can be used for the same number of subjects. We divided the main movements and the 5 repetitions into 4 signals for the training and 2 for the testing process. We will work on both datasets as they have the same acquisition protocol. Furthermore, dataset 2 and 3 classify the signals into 50 different movements, classified into 3 main exercises, B, C, and D, which is a relatively large number of movements compared to other datasets.
To understand the dataset, we used MATLAB software to draw the signal and make sure that we understand the properties of the dataset that we will use. The sEMG signals in the dataset are sampled at a sampling frequency of 2 kHz.
After seeing the representation of the datasets, we realized that there is a huge amount of data to deal with. So we decided to divide our goal, which is to classify the signals of 50 movements into subgoals. First, we will work on just 2 movements and test the accuracy of the classifier on them. If the accuracy was good enough, up to 80%, we will work on 8 movements and repeat the same steps until we will reach the final goal, which is classification for 50 movements. So we started by choosing our first 2 movements. After reading the dataset papers, we selected two of the basic movements of the fingers. The first movement is abduction of all fingers. The second movement is fingers flexed together in fist.
After choosing the movements that we will be working on in each stage of our project, we started preparing the dataset before starting the training process. In our data preparation stage, we first started by applying a function for choosing the selected movements in addition to the repetitions to be used for training the model. We then loaded all the data of the subject's movements and repetitions into a big matrix to make it easy to process the data and deal with it. And then comes the interpolation step, where we had to apply a linear interpolation function for the data to make sure they all have the same size before fitting them into the model. The final stage before the machine learning model is a pre-processing step that aims to stabilize the sEMG signal and reduces the size of the training dataset while maintaining neural information.
We were intending on classifying the signals by extracting certain features from the signal like mean absolute value, zero crossing, waveform length, and other features, then applying a machine learning algorithm to classify the movements. But after some research, we found out a different way to do this process, which is applying a deep learning algorithm. The basic goal of deep learning is to shift the emphasis from human feature extraction to automated feature learning. The state-of-art algorithm is CNN, Convolutional Neural Network for Pattern Recognition. Better performance, less processing and training time, and higher accuracies can be achieved by applying this model. The algorithm that we will be using is a DLPR, Deep Learning Based Pattern Recognition framework that uses convolutional neural network to improve the performance of sEMG based gesture recognition. First, we will be implementing the algorithm on dataset 2 and dataset 3, and finally make a model of hybrid data from both datasets. As an innovative approach to implement the processing, we will be using an FPGA to process the data instead of regular software microcontroller to ensure the highest possible speed. The classification of the movement is then sent to the control unit to drive the hand.
For the control unit, our work starts by defining a protocol to communicate with the signal processing unit to control the motors to perform a specific movement using a simple hand structure design. First, we receive bits, digital, from the signal processing unit depending on the number of movements, and these bits represent the movement number. The switch is acting as the input bits and its binary representation is acting as the number of selected movement in the table. As we mentioned before, the first stage we will use two movements only. So we will use only one bit to represent these two movements. Our first hand structure prototype can make 15 movements from the 50 movements. That's for the first stage. Then we will make a design to do all the 50 movements. And to perform these movements, we choose servo motor.
To sum things up, we're on the midway of creating a prosthetic hand based on EMG signal, empowering amputees to take part in more social activities, easily practicing their hobbies, enhancing their ability to create healthy relationships, and having an effective role in the community with real